Hello, I'm David Brannan. Films have often been used as creative tools with which to teach mathematics. One of the best-known examples is the 1939 classic The Wizard of Oz, particularly the famous scene where the Scarecrow gets his brains and recites Pythagoras' theorem, albeit incorrectly.
The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
Of course, the Scarecrow should have referred to a right-angled triangle, not an isosceles triangle, and to squares, not square roots, so that
the square of the hypotenuse of a right-angled triangle is equal to the sum of the squares of the other two sides.
In this podcast, we're going to take you on a mathematical journey called The Wizard of Oz, or OZ if you're American. It's a parody of The Wizard of Oz, and is based on an Open University radio programme. But instead of a scarecrow, talking tin man and cowardly lion, our Dorothy encounters some rather challenging mathematical concepts.
Integers, fractions, equations, oh my! Integers, fractions, equations, oh my! Integers, fractions, equations, oh my!
With the help of Dorothy, we'll meet fractions and complex numbers, including a rather colourful character I, before a climactic finale involving one of the most fascinating equations of all time, Euler's magical formula.
Bring down the witch's den, witch, oh witch, wicked witch, let them know the wicked witch is there.
Toto, I have a feeling we're not in Kansas anymore. Oh, dear, I've said that already. Who are these tiny creatures? Hello? Hello? Who are you?
We're the fractions.
Fractions? My, aren't you small?
Well, that's because we're proper fractions. We're less than a whole.
Isn't something less than a whole still a whole? You can't have half a whole, you know.
Not the empty sort of whole, the full sort. Unity, completeness, oneness, that sort of whole. Work whole, W whole.
Oh, are there improper fractions?
Of course. Over there. Look,
With the fraction standing on his head?
that's right. Any of us become improper if we turn ourselves upside down.
Of course, and there are so many of you.
So there we heard how Dorothy met the fractions. But what are fractions? And what's the difference between improper and proper fractions?
Well, David, we can explain fractions by describing a number line. First, we mark some point on the line that we call 0. Then, in one direction, to the right, we mark successive, equally spaced points as 1, 2, 3, and so on, just like a ruler. And in the opposite direction, we mark successive, equally spaced points as -1, -2, -3, and so on. That gives us all the whole numbers, or the integers. And then we start again. But this time, we mark equally spaced points in the positive direction at distances of 1/2 from each other. From 0, the first is called 1/2, the second 2/2, the third 3/2, and so on. In the opposite direction, we mark successive points as -1/2, -2/2, and so on. This gives us all the points on the line that represent fractions with denominator, that's the number on the bottom, 2. Some of them are repeats of the integers, of course. For example, 2/2 is the same as 1. Then we repeat this process for each whole number, q say, where the distance between successive points is 1/q, instead of a half. The points that we get then represent all the fractions p/q. If a fraction is p/q and q is bigger than p, then we say that the fraction is a proper fraction and p/q is less than 1. Otherwise, we call it an improper fraction.
And is that all the numbers there are?
No, there are lots more numbers that somehow lie between these fractions. The fractions are often called rational numbers because they're ratios of whole numbers. The other numbers are then called irrational numbers, not because they're illogical, but because they're not ratios of whole numbers. You can approximate these irrational numbers by a process of taking limits of rational numbers. Taken together, all these numbers are called real numbers. All real numbers can be written as decimal numbers, which are whole numbers plus so many tenths, plus so many hundredths, plus so many thousandths, and so on, possibly forever and ever. That's an example of a limit. Let's just look at the tenths, hundredths, and so on. the proper fraction bit. If we write the multiples of the tenths, hundredths, and so on, we get a whole sequence of numbers between 0 and 9 in succession. If the original number is a fraction, then these numbers eventually become a sequence of batches repeated. And we say that the decimal expansion is recurring. If the original number isn't a fraction, but one of the other real numbers, then the sequence isn't a set of repeated batches. And we say the decimal expansion is non-recurring.
Now it looks like Dorothy is about to meet a 300-year-old witch with a famous curve called the Witch of Ignacy. So let's see what happens.
I don't want to disturb anybody.
Well, you certainly disturb her.
You mean that angry old lady over there with the flowing bell-shaped cloak?
She's the Witch of Ignacy, a famous curve, almost 300 years old.
You'll regret this.
What's she so angry about?
She's misunderstood, or rather mistranslated. She's Italian, and her name is Versiera. That means turning.
That's not a bad name for a curve.
No, but she's been translated into English as Aversiera, which is witch.
Which is which? Oh, I see what you mean, which is witch.
Right, and she's been pretty unpleasant about it ever since.
I'm sure that if I'm nice to her, she'll help me. Versiera,
Versiera, not a Versiera.
can you help me, please?
Probably, but that doesn't mean that I'm going to. What do you want?
I want to get back to where I came from, please.
Back to your origin, you mean?
Please.
Well, I'm no use to you. I don't pass through the origin.
Oh, do you go anywhere that's useful?
Well, I approach the x-axis. The origin's on the x-axis, you know.
Is it? Well, yes, I suppose it is. So if I follow you to the x-axis...
I said I approached it, not that I got there. I'm asymptotic. I don't get there until infinity.
So do I have to go to infinity then?
Yes.
Why?
It spoils the story if you don't.
What's at infinity?
Well, the ends of things. Infinite things, that is. And the wizard.
The wizard?
The wizard of OZ.
Shouldn't that be the wizard of... Oh, no, I suppose it shouldn't. It would spoil the story.
You're learning. You trot off to see the wizard, and perhaps he'll help you get back to the origin.
Won't you come with me then?
Yeah, how can I? We don't start from the same place.
So where do you start from then?
From minus infinity, of course.
Minus infinity? Oh dear, this is all terribly confusing.
You'll probably find me along the way.
Oh, joining me, you mean?
No, of course not. Getting closer and closer the further you get along the x-axis. What do you think asymptotic means?
I really don't know.
I don't know what education's coming to these days. Get on your way.
Which way?
That way!
Which way? Follow the yellow brick road. Follow the yellow brick road. Follow, 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 follow the yellow brick road.
Can you explain infinity and minus infinity?
Well, if you start at any point on the number line and walk in the positive direction, that is to the right, keeping walking so that you pass every point on the line, then we say that you have gone to infinity. And if you walk in the opposite, the negative direction, keeping walking so that you pass every point, then we say that you've gone to minus infinity. Actually, this links with the idea of series, sometimes called infinite series. If you have a list of infinitely many numbers, then you can try to add them all up. So you write the first one, plus the second, plus the third, then plus the fourth, and so on forever. This expression is called an infinite series, or just a series for short. Sometimes the values of the successive sums get closer and closer to a particular number. In fact, indefinitely close as you go on. Then we say that the series converges, and the sum of the series is that number. For example, if you start with the list a half, a quarter, an eighth, and so on, and then add them up in this way, then what you get is a half plus a quarter, that's 3/4, 7/8, and so on. These numbers converge to 1. So the sum of the infinite series, a half plus a quarter plus an eighth, and so on, is 1. Otherwise, we say that the series diverges.
Actually, The Witch of Ignasi curve has nothing to do with witches, as you heard, but it's a very good name for a curve. Another thing, what did the witch mean by asymptotic?
Ah, this is where things become two-dimensional. You look at a plane, not just a line. So we take a horizontal number line in the plane that we call the x-axis, and a vertical number line that we call the y-axis. With the two axes meeting at 0 on each number line, we'll call that point of intersection the origin. Suppose next that you have a curve in the plane that meets each vertical line just once, and that goes infinitely far to the right. Now suppose that the vertical distance between the curve and the x-axis gets closer to 0. In fact, as close to 0 as you please, the further and further you go to the right. Then we say that the curve is asymptotic to the x-axis.
OK, shall we get back to Dorothy's search for infinity?
Oh, my. What a long way this is. And, oh, no, there's a fork in the road. Which way do I go? They're absolutely at right angles.
Howdy!
Who's that? Why, there's a strange little man standing a little way up this branch. Hello? Who are you?
Oh, I'm I.
I beg your pardon, I don't mean to be rude, but shouldn't that be I'm me?
Not at all. I'm I. Imaginary, you know? This is the imaginary axis.
Do I want the imaginary axis? I'm looking for infinity. I need to find the wizard. I was following the x-axis.
All axes lead to infinity, eventually. But it's dramatically more convenient if you stay on the other road, the real axis. Wait,
Where have you gone?
I'm over here, back where you came from.
Oh, what did you do then?
I squared myself. You know, I squared equals -1. I'm real now.
Weren't you real before then?
Not at all. I was imaginary.
I can't imagine what an imaginary number could be.
It's quite easy. Think of -1 like I am now.
Oh, I don't have any problems with that.
Now I'll take my square root. I'm back over here.
Oh,
I is the square root of -1.
oh, shouldn't that be I am the square root of... No, I suppose it shouldn't. So I should take the real axis then, that way?
That'll certainly take you to infinity. But I warn you, it's a long way.
Oh, dear.
Hey, never mind. I'll come along with y'all. Besides, I could ask the wizard to help me too.
What with?
Oh, I'm too simple. I get ignored. People don't believe in me. I want to be more complex.
A complex number. But aren't you already... Oh, never mind. I expect it would spoil the story. Don't you need to square yourself again then?
Oh, yeah, sure. There.
Oh.
Let's go.
We're off to see the wizard, the wonderful Wizard of Oz.
You're listening to Wizard of Oz from Fractions to Formulas from the Open University. We've just heard Dorothy meet an imaginary axis on her route to infinity. Can you explain I and the square root of -1 next?
Well, that brings us back to the complex numbers that Dorothy met earlier. We'll look again at the plane with the x and y axes in it. Any point in the plane can be described by saying how far along the direction of the x-axis it is from the origin, a distance x, say, and how far along the direction of the y-axis from the origin it is, a distance y, say. Then the numbers x and y are just the coordinates of the point. Now here's the cunning bit. The points on the x-axis correspond to real numbers. So let's call the points on the y-axis imaginary numbers. Then the point 1 on the y-axis we'll denote by the symbol I, where I stands for imaginary. So the point 2 on the y-axis is 2i, and so on. Then we'll denote the point in the plane with coordinates x and y by the single expression x plus iy. And we'll call x plus iy a complex number. And so that we don't lose all connection with reality, let's agree that complex numbers have to satisfy all the usual rules of arithmetic. That is, the rules for adding, subtracting, multiplying, and dividing numbers. And this works fine, just as long as we add the extra assumption that multiplying the imaginary number I by itself gives -1. That is, I squared equals -1, as you heard.
We should find out how Dorothy's getting on in her quest to get to infinity.
Oh, we've been walking for ages now, and it never seems to get any nearer.
That's the problem with infinity, you know.
Oh,
Not as easy as you thought it would be, eh? But there is a way.
well, how?
I'm not sure that a witch's advice can be trusted.
You speed up. Get faster and faster regularly. Look, in the last hour, you did 2 miles. In the next one, do 3. And in the one after that, do 4. And so on.
Well, I still think it will take forever.
Maybe. But it's something to think about. I'll be seeing you again.
I think I'm just going to go as fast as I can and see what happens. I'll race you to that pile of junk over there.
Hold on! Yes, that's no way to refer to a distinguished infinite series.
Who are you?
Why, me?
He?
Not he. E.
Is everybody in this country named after a letter?
Oh, it's variable, but most of us are.
Actually, I'm the exponential series or function. Everyone's so casual nowadays. But you can call me E. Most people do.
Well, can you help us? We're trying to get to infinity, but it seems to be taking rather a long time.
Well, I'm rather good at getting to infinity. You've heard of exponential growth, I presume?
Uh-huh.
Yes, well, I can get to infinity faster than anything else you care to name.
So if we went along with you, we'd get there quicker.
Oh, quicker, certainly, but it would still take forever.
Oh, dear, what can we do?
Let me think about it. I'm sure there's a way. Suppose we changed how we're going to get faster.
How?
Well, now we're just speeding up 1 mile at a time. Perhaps we could do better than that. Couldn't we go 2 miles faster in the next hour, then 4, then 8, 16, and so on? I'm sure there's something there.
I can assure you that no good will come of it. Why is I travelling with you?
He wants the wizard to make him more complex.
But isn't he already? Oh, never mind. I expect it would spoil the story. Does the wizard give people things they want?
So I'm told.
Then would you mind if I joined you?
Well, what do you want then?
To have some value. It's all very well being infinite, but I never seem to have any value.
But surely... Oh, never mind.
It would probably spoil the story.
We come to see the wizard, the wonderful Wizard of Oz.
There we met the exponential function. What's that? And E. Can you explain the value of E?
First E. Well, we have to use the shorthand term n factorial to represent the numbers 1, 2, 3, and so on up to n, all multiplied together. So 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, that's 6, and so on. So take the infinite series 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on indefinitely. It turns out that this is a convergent infinite series whose sum is approximately 2.718281828, and so on, and that's a non-recurring decimal. And we call this value the number E, also known as Euler's number. Leonhard Euler was a famous Swiss mathematician who became the court mathematician of Catherine the Great in St. Petersburg.
And the exponential function?
Right. Take the infinite series 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on indefinitely. This infinite series also converges, whatever value x happens to be, and its sum is e to the power x. That's an amazing fact about the number e.
Of course, we need E and I to come together with pi for Euler's magical formula, e to the I pi equals -1.
Oh, we've been using the witch's method for ages, and I'm not sure that she was trying to help us at all.
Just leave me alone for a bit longer. I'm sure I'm getting somewhere.
Well, we're not. Infinity is no nearer than it was before. and I'm getting very puffed with all this speeding up.
It's no better than if we were just going around in circles.
Speaking of going round in circles...
Why is that lion chasing his own tail round and around? He'll wear himself out. Hello? Who are you? Are you an imaginary lion?
Oh, no. I'm a real lion. There are lots of us lions around here. Parallel lions, intersecting lines, straight lines, curved lines. The lion at infinity...
Lion at infinity? Can he help us? We're trying to get to infinity to see the wizard, you know.
Oh, I'm sure he'd be useful. But he's the lion at infinity, you see. So he's not here just now. But this road's going the right way.
I see you're a real lion. Do you have a name?
I'm Pi. You see, I'm not a whole lion, just a lion segment. Not a very long one either, but a very repetitive one. I just go round and round in circles, round and round this unit diameter. I know it's irrational, but I'm very tired of recurring like this.
But surely... Oh, no. Never mind. That's obviously the way the story goes.
Do you think that if I came with you to the wizard, he could help me?
To stop recurring? Oh, yes. Do please join us. It's so nice to meet someone who isn't just a single letter.
I'm afraid that isn't true. It's my foreign ancestry. I'm not P-I-E, you know. It's pi. Greek.
What's the value of pi, then? And didn't we meet non-recurring before?
Well, the perimeter of a circle of diameter d is pi d. So the number pi is just the perimeter of a circle of diameter 1. And the value of pi is approximately 3.1415926535, and so on. A decimal expansion that never repeats itself. Another one that's non-recurring. And astonishingly, if you put I pi in place of x in the series for the exponential function, that's e to the power I pi, it turns out, after a bit of work, that the sum of that infinite series is exactly -1. And that's Euler's magical formula. E to the power I pi equals -1. And you can rearrange that formula as e to the power I pi plus 1 equals 0. A formula which involves the 5 most important numbers in mathematics: 0, 1, pi, e, and I. A remarkable formula.
Now they're coming to the end of their journey, which means we must be close to meeting the wizard and Euler's formula too.
And just who do we have here?
Please, sir, I'm Dorothy, and this is E, I, and Pi.
And just what do you all want with me?
I'm
Scarecrow, go on.
Oh, please, sir, if it's not too much trouble, I'm tired of being imaginary, and I'd like to be a little more complex.
And please, Mr. Wizard, I want to have some value. It's not a good life as a infinite series.
And I'm tired of recurring.
And please, sir, I want to go home. I want to get back to my origin. Please, sir, can you help us?
Oh, dearie me. What a collection of misdirected, non-problematic people we do have here. Oh, yes, what a collection. But a rather special collection, mind you.
Then you can help us?
Oh, yes. Come here, I
want to be complex.
But you are complex.
No, I'm not. I'm wholly imaginary.
It's all a matter of how you look at things. All you need is a different label.
And what label would that be?
Well, I think that this one, should do nicely.
0 plus 1 I. I'm complex. I'm a complex number. Oh, thank you ever so much.
Oh, nothing to it, literally. Now, let's see about the rest of you. You, Eve.
Yes, sir?
What's this about not having value?
Well, sir, I'm just a infinite series.
Just?
1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on.
Definitely.
I feel rather indefinite, actually. I could just go on and on forever. On and on to infinity.
Well, now you've got to infinity. You've added in all your terms. And I think you might find that you've got a value.
2.71828184.
Ah, better now?
Oh, yes, yes.
But don't tell everyone about it.
No.
It's not as easy as that for all infinite series. There are quite a few divergent ones around, you know.
2.71828184. I've got a value.
Now, Pi, what was your problem again?
Oh, I'm fed up with recurring over and over, just going round and round the same circles.
And you think that's what you're doing?
Yes, every 3.14159, I get back to where I started.
Every how many?
3.14159, 26535,
Go on.
89793,
Don't stop.
23846,
I haven't heard you recur yet.
26433.
Enough, Pi. You can go on all day, forever, and you will never recur.
Oh,
It's just a matter of how you look at things.
Please, sir.
Yes, Dorothy?
What about me, sir? I want to get back to the origin.
Ah, yes, I hadn't forgotten you. But this is something that I think your friends are better placed to help you with.
How is that, sir?
Pi, stop murmuring digits to yourself and go over there and stand next to I.
like this.
I, Pi.
I, Pi. We're getting there. Now, where's E?
He's behind you.
Oh, no, he isn't.
Stop this nonsense. E, get over there and exponentiate them.
E to the I pi?
E to the I pi. We're almost done now. There's just one more thing I need. Let me see, I need one of something. Ah, yes. Toto. You've had nothing to do in this story so far. I need to add one E to the I pi, but not yet. As soon as we do that, you'll be back to the origin, Dorothy.
How come, sir?
Well, as Euler, one of the greatest of mathematicians, observed that e to the I pi equals -1,
So that e to the I pi plus 1 equals 0, and I can go home now.
Indeed, my dear. And frankly, I think you should.
Is it possible to find out more about the complex formulas that Dorothy encountered?
At the Open University, we have a wide range of maths courses that explore the numbers and ideas that Dorothy encountered. Our introductory course, Y162, Starting with Maths, looks at fractions and simple formulas, while the course MU123, Discovering Mathematics, looks at the use of functions as models of real-world phenomena, including exponential functions, and other topics like applications of basic algebra. Then the second-level course, M208, Pure Mathematics, deals with real and complex numbers, as well as looking at functions, graphs, and exponential functions in greater depth. And the second-level course, MST209, Mathematical Models, uses complex numbers to help solve differential equations. Finally, the third-level course, M337, Complex Analysis, explains complex numbers in much greater detail, going all the way from Euler's magical formula to topics like complex functions applied to fluid flow and even fractals like Julia sets and the Mandelbrot set.
One last thing. What happened to the witch?
I think the wizard has the last word.
Well, that's just about that. Except that I think I can hear someone in the background. Vasiera, come on out.
I got here too late. They've gone.
Oh, really, my dear, you should try a more assiduous study of rates of convergence.
Well, now I'm here at infinity at last. What happens next?
Well, I think this could be the beginning of a beautiful friendship. Or was that a different movie?
The Wizard of OZ, From Fractions to Formulas, was presented by Professor David Branham and Professor Phil Rippon from the Open University. For more information and how to study, go to www.mcs.open.ac.uk.
If you enjoyed this clip, feel free to follow the links on screen for more interesting articles and free courses from the Open University.